Swayam Prabha. Digital India. Educated India.
Welcome back. Hello, everyone. This is a session on little more of embedded systems. We will be doing an overview of sensors and actuators and how they map to inputs and outputs, the kinds of sensors, how to read inputs. And I'll also briefly tell you about the memory architectures. The slides that I'm going to use as a part of this lecture series is by Professor Edward Lee and Professor Sanjeet Sechia, who also have co-authored the book on Introduction to Embedded Systems. These slides are available for download from their webpage and are copyrighted by them. So let's understand first what a sensor is and what an actuator is. Sensors are physical objects from which we read data. They measure some kind of physical quantity or the other, and they could be of various kinds. They are one link that we have. If you have to develop a computing algorithm or a platform as a part of an embedded system, the link that we have for inputs to your computing algorithm is a sensor. There could be several different kinds of sensors, but their goal is almost always to measure some physically measurable data and pass it on through a communication network. On the other hand, an actuator also helps us to talk to physical quantities, but it is a device that helps us to write back or modify or pass a command back to the physical quantity. So a sensor is something that helps us to read from the physical quantity. An actuator is a device that helps us to write back to the physical quantity. Here are some examples of sensors and actuators. Cameras, which are widely present from our phones to anywhere else, are one of the most powerful sensors because they can record video, they can record snapshots, audio, and everything. Accelerometers, gyroscopes, strain gauges, microphone, magnetometers, sensors for chemical entities based on the chemical plant that one is working on, sensors for temperature, pressure, light on and off switches, switches that turn on or off a pump, valve, and so on. Several different sensors exist. These all provide inputs for depending on the functionality that we want for the cyber-physical system. Actuators, what could be it? A lot of devices that we can control are actuators, motor controllers, solenoids, light emitting devices, lasers, LCDs, speakers, switches that can be put on or off, valves that can be turned, opened, or if it's an analog thing, adjusted to be partially open or partially closed, and so on. So, fine, there are so many sensors that we can read data from, so many actuators that help us to provide data to control the devices. What is the issue if we try to work with them and develop an embedded or a cyber physical system with them? The first thing is they represent physical devices. Physical devices exist as physical phenomena. They exhibit physical phenomena. We need appropriate modeling mechanism that will help us to model data as we read it from the physical devices, sometimes the variation in data as we read it from the physical devices. There could be a lot of noise due to various kinds of disturbance in the measurements recorded and provided by the sensors. We need appropriate noise elimination techniques to make sure that we read the right kind of data from the sensors. There could be bias because of wear and tear, because of battery, several different issues that on the data that we read to the sensors. So that's another thing that we have to cater to. The rate at which we sample the data from sensors, how frequently we do it. Do we do it every second? Do we do it every millisecond? Do we do it every hour? Do we do it once every day? That also influences the quality of data that we get from the sensors. The communication network, the fact, are they faulty? Are they not faulty? Lots of issues are there about the sensors. So let's take examples of the kind of projects that are popular where embedded systems come and understand how sensors play a role. These are examples of self-driving cars. They existed as long as late as 1999. And recently, we all know that several companies are into self-driving cars. If you notice, they are not meant on general roads, they drive on designated roads. So be it. This is another example of an autonomous driving vehicle, not a self-driving car, but imagine this being so useful in a stormy situation where it's very difficult for a human to control it. The data that it measures could be different. The kind of details that it gets could be different from this kind of scenario where there is ideal light, there is not snow, and there is no traffic in the front, and so on. So if I take a car and look a little bit into it from the point of view, from the lens of understanding what sensors does a car have, this is the kind of functionality or the sensor that the car has. The blue colored ones are applications that cater with mainly radar information. And the yellow ones are the applications that cater with sonar, sound related information. So there are in a sensor rich car, that is in a car that is filled with all kinds of sensors, the scope of applications that you can develop by reading and processing data from these sensors is what this slide provides. So you could talk about lane departure warning system, you could talk about a blind spot detection system, you could talk about lane change assistance, and so on. Several different applications can be provided if we have the right kind of sensors in the cars. So this view is the kind of sensors and the processing that you can see in a typical sensor-rich car. So there could be radar sensors that are located on the front side of the car. There could be a video camera which monitors the vehicles and the surroundings that it is accessible by the camera. There could be a light detection and ranging sensor that is used to monitor the surroundings. Obviously, cars have GPS system, which we all use. There could be ultrasonic sensors. There could be odometric sensors. And there is a central processing computer in the car that deals with the data from the sensors and processes them, and where our algorithms that we talked about that were present in this slide might be executed and will reside on. The slide also gives information on the cost of sensors, color coding them based on how expensive or cheap they are, just to get you an idea of they cannot be readily available as and when we want it. So this is the same thing in development of a snow mowing vehicle and the kind of technology that goes into it. So some of the sensors that go into these kinds of operators are listed in the slides below. Magnetometer is one of the most common sensors. On the right, there is a Wikipedia image on the physics of a magnetometer. There are charge particles, which are basically charged electrons, which are these things labeled as one, which flow through a conductor, which is this part created in two. And because they do that, they serve as a sensor. Magnets around the south and the north pole marked as 3 induce a magnetic field that causes the charged particle to accumulate to one side of the sensor, which induces a measurable voltage difference from top to bottom. And the sensors actually measure that only. A magnetometer works by creating such a scenario that causes a measurable voltage difference that can be measured and output as a sensor measured value. Suppose we take something like this, which is a magnetometer. What could be the problems that it suffers from? The first problem is aliasing. Sample data is vulnerable to aliasing, where certain high frequency components will masquerade as low frequency components. And to overcome this, we have to consider careful modeling of the signal sources, the analog signal conditioning, or digital oversampling that are necessary to counter this effect. Let's understand a little more about how certain sensors work. Other kind of sensors that are popular are accelerometer. What are the uses of accelerometers? They are used for navigation, for change of orientation, for detecting if something is fallen, for stabilizing an image. They are used in automatic airbag systems, and so on. The simplest accelerometer works like this. There is a distance between a plate that is fixed to the platform and another plate that is on top that is attached to the platform by a spring and a dampener. The measurement is typically done by measuring the capacitance, and that's what is output as the sensor value. In a spring mass damper accelerometer, It's the same picture that we saw in this slide, which is presented like this. The physics that is followed is Newton's second law, which is force is mass into acceleration. The kind of force that is applied could be different based on the accelerometer that you want to consider it as, but the force is balanced by the restoring force of the spring. So this is, if you go one step down, if I understand what is the physics of the spring mass damper system, these set of equations tell you what are the forces that act in the dampener: force due to spring extension, force due to viscous damping, and how Newton's second law applies on both the forces put together. So we take these kinds of equations, we convert it into an integral equations, we write initial conditions, we deploy lookup tables, and those lookup tables are what goes into our software implementation. You can use the same sensor to measure tilt, in which case the equation becomes as what is given here. You can use other sensors, and you can use micro level accelerometer, in which case the equations change drastically, and so on. So for each kind of sensor, we look at the kind of sensor that is there, understand the high level physics or the dynamics of it, consider the equations, try to model or fit the curves of these equations using appropriate lookup tables, by which the equation or the physical phenomenon gets discretized. And that discrete entity is what we consider for our software implementation or for our algorithm to process on. One more popular sensors are gyroscopes. Gyroscopes are used for measuring changes in the orientation. The figure here gives a typical example of a gyroscope, and it's schematic of how it works. If it's an optical gyroscope, they leverage a certain kind of effect where a laser light is sent around the loop in opposite directions and interference is measured. When the loop is rotating, distance the light travels in one direction is smaller than the distance in the other, and that change is what is measured by the sensor. INS sensors, INS stands for Inertial Navigation Systems, as another popular combination of sensors that use our global positioning satellites, GPS satellites, which is now inevitable and famous. They are a combination of GPS sensors. In addition to that, they have a 3-axis gyroscope for measuring orientation, and they also use accelerometer for correction after the orientation. So this is a combination of 3 sensors which caters to an inertial navigation system. And these sensors have problems. There could be drifts as if they're using in the aircraft. So we have to adjust the drift. We have to make sure that the data is right. It all depends on the application that you're going to use it for. What are the various design issues that people typically deal with while reading data from sensors as a part of a cyber physical system application? This slide lists all the issues. There could be issues related to calibration, issues related to non-linearity, sampling, noise, and failure. What do we mean by issues related to calibrations? As I told you, sensors always measure physical phenomenon, changes in physical phenomenon, and send it back to us. How am I going to consider it? What is the unit that I want it to be measured on? And what is the unit that my algorithm will work on? How do I relate if there are replicate sensors that measure the same physical phenomenon? And how do I take the best value that is possible from the various sensors? All these things dictate a lot. What if a sensor fails? How do I create backup sensors? How many backups do I need? Based on the cost, based on my weight, several different constraints are there. As far as non-linearity is concerned, typically, a lot of physical phenomena are what we call non-linear in nature. They exhibit non-linear behavior that is not always represented by a straight line. Measurements taken by sensors may not be proportional to the physical phenomenon, mainly because of sampling. We sample them at certain rates, at certain frequencies, and in between the sampling intervals, we actually lose track of what happened in the physical world. So we might need some corrections to make up for that, and we might need to cater to feedbacks that result as a because of this. Also, when it comes to sampling, as I told you earlier, there could be aliasing, that's a problem. We could have missed certain samples because there wouldn't have been a change in the physical phenomenon at the frequency with which we sample. There are several issues that come. There is also an issue of noise because, again, physical phenomena is in the analog world and it will have to be converted eventually into the digital system for us, our computer algorithms, to be able to process it. So, noise is a big issue that comes into picture. Sensors could also fail because they are, after all, hardware devices. So, because sensor fails, we usually keep redundant copies of the sensors. If you keep two copies or three copies of the same sensor that is meant to read the same kind of data from the same physical phenomenon, how do you decide which sensor's data to use? So there are sensor voter algorithms or sensor fusion algorithms that help you to decide which sensor data to use. In addition to that, they can also be subject to attacks. One famous attack that has happened in the past is the Stuxnet attack, and we have to be prepared to cater to sensors that fail because of attacks on them. So these slides go ahead and talk in detail about sensor calibration and about failures in sensor. When it comes to sensor calibration, there are several models that have been present in the literature. There is an affine sensor model, and we also cater to bias and sensitivity. I'll skip these, but they're usually, when you buy a sensor, you will get these data sheets which talk about what the sensor input is, what is the minimum range, what is the maximum range, what is the unit with which it is measured, what is the sensitivity of the sensor, what is the base level, what are the noise, and at what frequency the sensor responds in what way. So these kind of data sheets help designers design appropriate parameters by which they know how frequently to measure the data from the sensors and what happens to it. As I told you, after calibration, we elaborate a bit on failures. And let's go on to that. So, as I told you, sensors are, after all, physical devices. Like all physical devices, they suffer from wear and tear. They can have manufacturing devices. They can be subject to tough weather conditions. And they will have a shelf life after which they will stop working or maybe run out of battery or get rusted. There could be several different issues. So we cannot assume that all the sensors present as a part of my system will work correctly at all the times. So we have to keep redundant copies of sensors. Then comes the trade off. How many copies? If I have more than one copy, how do I know which of these sensors data do I use from? Can I take an average of them? How do I take an average? All these questions come into picture. Here is an example of what could go wrong because of not taking the right kind of average. In the year 2008, an Airbus A330 aircraft, as a part of Qantas Airways, in its flight from Singapore to Perth in Australia, suddenly started pitching violently mid-air. There were passengers who weren't wearing seat belts. They literally jumped out of their seat and hit the ceiling of aircrafts, which resulted in 12 serious injuries. So it was counting as an accident. When they investigated into why this happened, the problem was grounded down to sensor fusion problem. So there are sensors which measure what we call the angle of attack, AOA, in an aircraft. And because these sensors can malfunction, there are redundant sensors available. Three angle of attack sensors were available, one on left side of the aircraft and two on the right side of the aeroplane's nose. Now, between these three sensors, because we use the same three sensors to measure the same value, which is the angle of attack, we would like to get a good consensus value, and that's where the problem is. This consensus value have to deal with the algorithms for them, have to deal with inaccuracies, positions of the aircrafts, spikes, failures, and so on. So, in this particular angle of sensor attack, not attack, failure, it was sampled at 20 hertz frequency. And then they compare each sensor to a median of the values of the three sensors. And this was the algorithm that they used. If the difference is larger than some threshold for more than 1 second, then a sensor is flagged as faulty and ignored for the rest of the flight. Assuming that all the three sensors are working okay, the mean of the first and the second sensors are taken because one is on each side of the aircraft, And if the difference between the first and the second sensor and the median is larger than some set threshold, then the previous value is used for 1.72 seconds. So you can imagine takes a lot of technicality, domain knowledge to come up with such a decision. But this was the algorithm that they deployed for processing data from the redundant sensors. What caused the failure? That's what is given here. There were two spikes in the first sensor. The first spike shorter than 1 second, second still present 1.2 seconds after the detection of the first. As a result of this, the flight control computers commanding a nose down aircraft movement, which resulted in the aircraft pitching down to a maximum of 8.5 degrees centigrade suddenly. This caused the accident. So, how to deal with sensor errors? There is a lot of ongoing research on this. There are several standard algorithms available, but whether it applies to our setting or not is still subject to rigorous analysis and trial and error and research. One possible approach is that in an intelligent sensor, ask it to communicate a range of values as an interval, but not one value. But then, it depends on whether you need it and how good the width of the interval is and how good the sensor is, and so on. So, one of the popular sensor fusion algorithms is Marzullo's algorithm. I will just tell you what it is. I won't go through the details. So, the premise or the axiom by which the algorithm works is that if a particular sensor is non faulty, then assuming that we do interval measurement, its interval contains the true value. And once what I observe, when based on what I observe, I should be able to conclude that the true value must be overlapping in the non faulty intervals. And here is the algorithm that I arrive to get a consensus. I choose interval that contains all overlaps of n minus f, where f is the number of faults and n is the width of the interval. That is, from the least value of least value contained in the n minus f intervals, I go to the largest value that is contained in n minus f. So here is an example of how it works. Let's say we have four sensors, S1, S2, S3, and S4. And if the sensor is working, they measure the same value. And if the sensor is working right, you expect it to measure or report values in this interval that is marked out as a probable value. So clearly what is happening here, the sensor S4 is way out of range. S1 is partly out of range. S2 to start with is okay, later gets out of range. S3 to start with is slightly out of range, gets into the range, and then out of range. So these are the interval reports of the range of possible values. Out of S1 and S4, definitely one of them is faulty. And between out of S3 and S4, definitely one of them is faulty. Because S4 comes in both the cases, S4 is faulty. So you use values from S1, S2, and S3 to be able to come up with a sound estimate of what these four sensors measure. So there are different cases in which they use Marzullo's algorithm. There is one more algorithm by Schmid and Schossmeier. All these algorithms have been time tested. I won't go through them. This is an example of a different kind of sensor, which is not used in an aircraft, but it tells you how subtle the data measured by the sensors are. This is a bionic hand, which is meant to replace amputated human hands. And this bionic hand has got such fine precision measurement. It's an expensive device, but it's got 5 DC motors, which act as actuators. It can grab a paper cup, let's say, which holds a drink, and not crush it. It can hold a key, insert it into a lock, and turn it. As you see, it holds a coin. It is controlled by the nerve impulses of the user's arm, combined with autonomous control to adapt to the shape of whatever it is grasping. So this is another sensor-rich embedded system. So I'll move on and end at the summary. So we looked at several models of sensors, briefly studied accelerometers, looked at how to measure data from several sensors, briefly understood what the algorithms are. So that was an overview of sensors. Let me move on and tell you how these sensors map to inputs, outputs, and interrupts in an embedded system. Again, these slides Acknowledgement for Professor Edward Lee and Professor Sanjeet Seshia, who wrote a book on embedded systems and taught this course at UC Berkeley. So as I told you, we just saw several sensors which exist in the physical world. Physical world is a continuous world. There are no stops. Everything moves in a continuum as far as time is concerned, and several things happen concurrently. As I am recording this lecture, somebody else might be doing something. Somebody else might be doing something else. A lot of things happen concurrently. Whereas, contrast it with the cyber world, and that is the world in which we write our algorithms, we implement our code, and run our cyber physical systems. Everything is digital, which means everything is going to be discrete, not continuous. So you're going to lose the pending data from discrete to continuous. Things are also going to be sequential because there is nothing like a concurrent thing in a cyber world. So, in terms of practical issues, what are the issues? Sensors measure analog data, which have to be converted to digital data for our processing. Sensors could be wired or wireless, they come with their own challenge. They could be connected through serial ports or parallel ports. As I told you, they could be sampled at regular intervals or they could be sporadic, triggered by the presence of an event. The rate at which you sample them matters. How secure are they? Who has access to that kind of data? That also matters. What are the physical connections between them? What is the electricity requirement between them? All these things go into design and architecture of a cyber physical system. So let's take an example. If I take a board, microcomputer board called BeagleBone Black from Texas Instrument, this is what it has. It has all these ports. It has a micro HDMI. It has a USB. It has a serial debug. It has DC power, Ethernet, another USB, MMC, boot button, so many things, right? All these have to be used, or a subset of them have to be used to read data from the sensors, convert them into inputs, or generate outputs from the process, computer programs that run on the processes, and convert them into signals that can be used for controlling the actuators. So I can attach these things and make an Arduino board out of it. I can do more attachments and do something like this. And then along with the configuration, you will have all these data sheets that you get into picture. And this is how the memory looks like. And then you start looking at the diagram and how to turn on the LED, what should you do, and stuff like that. Like, for example, when I turn on the LED, assume that my GPIO pins can sync up to 18 milliamps. Assume the LED, when forward biased is turned on, has a voltage drop of 2 volts, which is the resistor that you should use. So that's the kind of decision that you take to be able to do with your actuator and your sensors. In terms of connections, you can have parallel connections, one wire per bit. You can have serial connections, which is one wire per direction. There are several serial ports that are still popular, RS-232, USB, we all use them even today, or they could be mixed kind of connections. Parallel connections these days, as I told you, have been replaced by serial connections. You can think about why so. In serial interfaces, for example, if you take RS-32, it supports what we call an asynchronous serial connection, where the hardware clock is not common. There are RS-232 is replaced by USB, which is simpler but more complex protocol, or Bluetooth, which is completely wireless. Similarly, you have a UART receiver transmitter. And then how do I read input-output mechanisms? As we told you, sensors read from the physical world. We would want to use them in our cyber world or in our computing world. So how do we do it? Physical world is continuous, computing world is discrete. So we use polling as one mechanism. We also can use interrupts as the other mechanism. To start with, what do you do in polling? You basically have a main loop which periodically, at what frequency, at what period, that you design based on several other parameters, but it periodically reads input output data. If an output needs to be produced, it will produce it. If an input is ready, it will read it and convert it. So here is how one polling works. Then you look at the processor setup code. It checks for IO control register. Let's say it has one peripheral, 1, 2, and 3 peripheral. It checks for status of peripheral 1. If it is ready, then it services the input or output at peripheral 1. If it's not ready, it goes and checks for peripheral 2. If it's ready, then it services that. If peripheral 2 is not ready, then it goes and checks for peripheral 3. If it is ready, it services that and keeps repeating it. That's this outer loop. And keeps doing this forever based on the frequency with which you ask it to do. So this is a classical example of how polling works. So if I have to write code for that, here is an example. Let's say I have an Atmel AVR 8-bit microcontroller and I want to send one byte of data over a serial port. Then I write code like this. Here, X is a variable which is of type unsigned 8-bit integer. UCSR 0A and UDR0 are variables that are defined in the header, and they refer to the memory map register of the UART transmitter receiver. Suppose I have to send a sequence of bytes. Here I do this while not, but I know a priori the sequence of bytes that I have to do. Then I add a for loop to the front. So I say for I equal to 0, I less than 8, I plus plus, do this. You can think about what will happen, how long it will take to execute. That based on the board speed, the processor capacity, and so on. Suppose I have to receive on a UART port, then I write the same thing and I do a return value and so on. So another way to do it would be using interrupts. What will happen in interrupts? Interrupts can be viewed in two ways. One is to say that they correspond to sporadic inputs. It doesn't come so regularly that I need to run periodic polls to read it, but it comes sporadically. So I view it as an alert, wait for an interrupt, and then read it. Or there could be an error, and then for that also I use an interrupt. So here is how a typical interrupt works. To handle interrupts, programmers write what we call ISRs, interrupt service routines. And an interrupt always, even though the word indicates that it could be an error, please remember that it is not always an error. It could just be something simple like waiting for a sporadic sensor input to come. So we write the interrupt service routine, which is a piece of code that we write to handle the interrupt. We register the interrupt service routine. And when the interrupt comes, which is given by this arrow, what happens? The processor executes the interrupt service routine by doing a context switch. When it finishes executing the interrupt service routine, it resumes to doing whatever normal code that it was doing. So there could be various kinds of interrupts. There could be triggers, there could be responses. The trigger could be a level change on an interrupt request pin or writing an interrupt pin configured as an output. Responses could be to disable interrupt, to push the program counter onto the stack, several different things. ISRs have to be designed very carefully, and it should be designed in such a way that they don't end up eating into the main functionality. But the problem is with ISRs, they make computing very non-deterministic. So you have to be careful. So here is an example of a timed interrupt. So my ISR gets registered and then a timer gets initialized. Timer keeps ticking its own time. And when the timer finishes, you process the interrupt. And when you process the interrupt, you might be executing some task code. You come out of it, you update your tick and sample, which is the ISR, and then you go back to executing task code. So you can set up a timer on a particular processor. You can set up a timer on another kind of processor. These are examples for that. I'm skipping them in the interest of time. Yeah, so while handling interrupts, you have to be careful for interrupts not taking too much time because the main code's functionality still has to run. How much time will it take to switch for context? If there are more than one interrupts, do I prioritize one over the other? How do the interrupt service routines interact with the applications in terms of priorities and taking over and passing back the control? How do the interrupt service routines interact amongst themselves? All these are issues that we have to handle. So that was a brief on memory. Let me move on. That was a brief on inputs and outputs. Let me move on and talk to you for the next few minutes on memory architectures in embedded systems. What is the role of memory in embedded systems? Fine, we read data from sensors and actuators. We process them as inputs. We also have to store and process them for further use. We might have to store and communicate it to other applications and so on. So, how much do we do and what can we afford? So, typically, when I'm looking at memory, these are the issues that we handle. What are the types of memory? Is it volatile or non volatile? Volatile versus non volatile means that am I going to remember things when there is no power, or am I going to remember things only as long as there is power? Is it SRAM or is it DRAM? What is going to be my memory map? Is it going to be based on a certain kind of architecture? Is it going to be based on input output? How is my memory going to be organized? Is it going to be statically allocated always? Is it going to be dynamically allocated? Am I going to use a stack? Am I going to use heap? How am I going to collect garbage? How am I going to clean up the memory? Lots of these issues come into picture. What are memory hierarchies? How is memory produced and managed? Lots of examples are there. When it comes to non volatile memory, as I told you, it means that it's a memory that preserves, retains, and stores content even when power goes off. These are the kinds of non volatile memories. There is erasable, programmable, read only memory, which is an old one. There is electrically erasable, programmable, read only memory. There's flash memory. There are also disk drives. We clearly cannot rely on disk drives for embedded systems because it won't meet our real time constraints. In terms of volatile memory, which loses its content when there is no power, static random access memory is there, which is fast and it's static, so it's deterministic, but it consumes a lot of power. It's used for caching, scratch pads, and small embedded services. There's dynamic RAM, which is much slower than static RAM, but it's denser, it has higher capacity, and that typically becomes the main memory. In addition to these two, there is memory that the bootloader exclusively uses on power up. So this is how an example of an ARM Cortex microcontroller with a 1 MB flash memory by ST Microelectronics looks like. This is the memory map, which tells you here are the peripherals, here are the external devices that are stored. This is the memory for data. There is more memory for peripherals, memory for data, and then flash. The split is like this. These are the addresses, and this is how it is split. Yeah, so I'll move on. And so here are examples of more memory. So this is an Arduino board, which is very popular in the context of IoT. It's a family of open source hardware boards built around 8-bit AVR processors or 32 ARM processors. This is an Arduino board that is built on Atmel AVR processor. These are inventors of the first Arduino Uno boards, which are very popular in small level IoT systems. Here is another example of an AVR processor that uses an Atmel microcontroller. This is a memory map for that, and so on. So there are some questions that you might want to test. And how do I organize memory for my program? As I told you, when you run a program in memory, you could statically allot memory, in which case the compiler chooses the address at which to store a variable. You could use a stack, which is a dynamically allocated memory, but that works like a stack. That is the last to be in, is the first to be out, push and pop. Heap, which is a dynamically allocated memory, which works in its own style. So here are some examples of statically allocated memory. So suppose I have a function like this. There's a function called foo, which says static x is a character that is declared statically. Compiler chooses what is the address to use for x, but the variable is local to this function and meant to be accessed only within this function. The variable's lifetime is the total duration of program's execution, but it is accessed only by this function. Yeah, so I'll move on. There are lots of examples which you can refer to. These slides are publicly available. Yeah, so let's maybe look at this example. There is some code which talks about variables being declared and memory being used, and your goal is to find a flaw in this program. So there is an integer variable x which is initialized to 2. There is a function called foo. There is a function called main where a function called foo is called with the value 10. Foo uses a local variable integer. It does something and returns the z. So pause for a couple of minutes here and think about what could be a flaw in the program. The flaw is related to where each variable is allocated. So here is what is the problem. So if I take this statement like this means that variable x is statically allocated. Compiler assigns a memory location. If I take the parameter y, which is a second variable, it's passed on as an argument on the stack. Z is a variable that is internal to the function foo, so it's an automatic variable on the stack. Whereas if I call it here, the program counter, argument 10 and Z go on the stack and maybe along with something else, depending on the computer. On the compiler, the procedure foo will return a pointer to the variable on the stack. And if there is another procedure call or interrupt that occurs before the return pointer is dereferenced, then you've lost the value. So that's the flaw in memory mapping. There could also be issues related to recursive code. Several different issues are there. And there is a bit about memory hierarchy, which also I'm skipping in the interest of time. And there is a direct memory map and so on. So hopefully this overview would, even though it was quick, would have helped you to understand how memory works. Similarly, you can talk about processors, scheduling algorithms, how a real-time operating system works, and so on. In the interest of time, because we would like to move on to IoT and understanding IoT, I'll stop here and I'll point you to this wonderful book on Introduction to Embedded Systems by Lee and Seshia, whose slides we have used. Thank you.